Sections 2.1 and 2.2 of your textbook tell the story of the evolution of atomic theory. Where do we get this idea that atoms are made up of protons and neutrons and electrons, and what makes the atoms of different elements different elements? So it's really a fascinating story. I've sort of summarized here what your textbook is saying. I would definitely recommend going through the textbook and also watching the videos that I've linked. Week 1 videos had a few videos about Antoine Lavoisier and how the conservation of matter overturned the theory of phlogiston that had been prevalent up to that time. So that is an interesting story. And then other clips in the mysteries of matter focus on Rutherford and Moseley and how the nucleus was discovered, and also atomic numbers, how that pattern was discovered as well. And so those videos make the story a lot more dramatic and interesting than my outline here can make it. All right, so I just wanted to make a comment on these laws of definite proportion and multiple proportion. We'll look at that in a moment. We'll do some problems on those to illustrate what these mean, and also the law of conservation of matter. These are laws because, again, they're mathematical patterns. The matter going in equaling the matter going out. That's a pattern. The law of conservation of matter doesn't try to explain why matter is conserved. It's just a mathematical pattern that has been formulated and is a law. The same kind of thing with these other laws. These are mathematical patterns. The atomic theory is trying to explain why we would see these results and these patterns in our experiments. And so it was a theory, a model to propose what matter is made of, why it behaves in this way based on a model of what Dalton proposed. And it was fairly accurate considering the time. There are some things that have changed and been modified slightly, but I think that we can say that we still use atomic theory even though it's been elaborated and built on. So the theory is that you can cut matter down to smallest pieces that cannot be cut any further without changing what the substance actually is. So the atom is the smallest unit that an element can be and still be that element. That an element consists of only one type of atom. This has been slightly modified because we know we have different isotopes of the same element that we'll talk about more in this chapter. Atoms of one element are different from atoms of all the other elements. Now we know that that's based on the number of protons that that atom has. At the time, that was not known. A compound consists of atoms of 2 or more elements in small whole number ratios. At the time, we didn't have chemical formulas, but the chemical formulas that we write today follow this model that Dalton proposed. And then we have the observation that the atoms rearrange to yield different compounds, but the amounts that we put in are going to be the amounts that we get out. So that reflects the law of conservation of matter that we've seen before. Let's go ahead and look at these problems which illustrate the law of definite proportions and the law of multiple proportions. Okay, so I've added in the law of definite proportions and the law of multiple proportions here. The law of definite proportions saying that if you have two different samples of the same pure substance, that pure substance will have the same mass ratio of elements every time. So we have these two substances, X and Y, and we're trying to see if they could be the same substance. If they are, they would have the same mass ratios of carbon to hydrogen. So let's figure out what the mass ratios of these two substances, X and Y, are. So this first substance, X, to figure out the mass ratio of carbon to hydrogen, we take the mass of carbon and divide it by the mass of hydrogen to figure out the ratio. We have a 30.6 grams of carbon and 6.85 grams of hydrogen compound. And so we can see that the mass of carbon is 4.47 times as much as the mass of hydrogen. And then for substance Y, the mass ratio Y has 23.4 grams of carbon, 5.42 grams of hydrogen. And so it's not very obvious to look at this ratio and see that they're the same, but if you actually do the division of both of them, you can see that substance Y is also 4.47 times as much carbon as hydrogen. And so these are the same ratio. They could be the same. So anything that is the same has the same ratio, but something that has the same ratio could still be different. So it's always one way, but not always the other way. So these could be the same, but they might not be. So our conclusion here is that it is possible that they are the same, but they don't have to be. If these were different, then there's no way that they would be the same if they were both pure. All right, let's take a look at the law of multiple proportions. So that means that sometimes two elements can form two different substances. And if two elements can form two different pure substances, or more than one, possibly three, so two or more pure substances, these substances, since they are different substances, will have different mass ratios of the two elements. But the mass ratios that you find will be small whole number multiples of each other. So we've done the analysis of the mass of copper to oxygen in one of the substances and found that the copper is 7.94 times as massive as the oxygen in that sample. So similar to how we got 4.47 above, now we've gotten 7.94 as the mass ratio. And so if there's a different substance made of copper and oxygen, then we will find a different ratio, but it will be a small whole number multiple of this. Or this will be a small whole number multiple of the other ratio. So if we look at A, the ratio A, 8.94, is not a small whole number multiple of 7.94. These do not multiply. This one is not double that one is not double this one, nor are they 3 times one another. So this is not a small whole number multiple of 7.94. 79.4 is a multiple, but it's not that small. It's 10 times as big. So let's keep that in mind and keep going here. 3.97 is half of 7.94. You can try, dividing one by the other. It comes out to be 2. So this one is, the 7.94 is a small whole number multiple of the 3.97. So these are related to each other in a very simple whole number mathematical relationship. And then finally, this one over here is just the inverse of 7.94. So this is not a small whole number multiple of the other one. So these are not simply mathematically related either. So this one is 0.5 times as big as the other one. So these two numbers, the 3.97 and the 7.94, are small whole number multiples of each other. So this is what we mean by that law of multiple proportions. And this one is just sort of a check on whether you've watched the story of Rutherford's experiment or read the story of Rutherford's experiment and figured out what we've learned from that. When he saw the alpha particles bouncing back, Rutherford proposed that the positively charged regions must be very concentrated in a small percentage of the total volume in order to make a concentrated positive charge that could repel the alpha particle.